The eternal silence of these infinite spaces frightens me. Blaise Pascal. In the summer of 1950, four physicists walked to lunch at Los Alamos, the secret town where the first atomic bomb had been built. Enrico Fermi was with Edward Teller, Emil Konopinski, and Herbert York. Newspaper reports about flying saucers had become a public craze. A recent cartoon in the New Yorker blamed aliens for the disappearance of public trash cans in New York City. The scientists joked about it as they walked. Then the conversation moved on. Sometime later, while they were eating, Fermi suddenly asked, "But where is everybody?" His companions knew what he meant. The Milky Way is old. It contains hundreds of billions of stars. Even if planets were rare, some should have formed billions of years before Earth. If intelligence had appeared on only a small number of those worlds, one civilization might have learned to travel between the stars. It would not need impossible engines. It would not need to move faster than light. It would only need to keep going. Imagine a ship crossing the space between nearby stars at 30 kilometers per second. That is fast by present human standards, but painfully slow beside light, which moves 10,000 times faster. A journey to another star could take tens of thousands of years. When the ship arrives, its passengers build a settlement. Give that settlement 100,000 years to grow, learn, and decide what to do next. Then it sends two ships to two nearby stars. Each new settlement eventually does the same. The process begins slowly. For a long time, almost nothing seems to happen. Then the number of settlements rises because every new world can become another starting point. Even with cautious assumptions, the wave can cross the Milky Way in far less than 1 billion years. More ambitious models produce times of only a few million years. The exact number depends on the speed of the ships, the delay between arrivals and new launches, and whether every settlement keeps expanding. The important point is the scale. The Milky Way has existed for more than 13 billion years. A billion-year settlement process could have happened many times before the Sun formed. If one old civilization had started early enough, its machines, settlements, or ruins might already be everywhere. Yet when we examine the solar system, we do not see obvious alien cities. We have found no machine waiting on the moon, no clear signal in the sky, and no evidence that Earth was visited by an advanced civilization in deep time. Reports of strange objects are not the same as evidence. A mystery becomes evidence only when it survives careful checking and rules out ordinary causes. Nothing has passed that test. That gap between expectation and observation became known as the Fermi paradox. Strictly speaking, it is not a logical paradox. The laws of reason do not promise us aliens. It is a conflict between two impressions. Intelligent life seems as if it should be common, yet the universe looks empty. The first impression needs to be examined before the second one can disturb us. In 1960, the astronomer Frank Drake pointed a radio telescope in West Virginia toward two nearby stars, Tau Ceti and Epsilon Eridani. His experiment was called Project Ozma. The name came from the imaginary queen of the land of Oz, a distant ruler in a strange country. Drake listened for a narrow radio signal, the sort of clean tone that nature would be unlikely to make by accident. An early alarm appeared, but it was probably aircraft radar. The rest was static. The following year, Drake organized a small meeting at Green Bank. He needed a way to arrange the discussion, so he wrote 7 factors on a blackboard. Multiplied together, they gave an estimate of how many detectable civilizations might exist in the Milky Way. This became the Drake equation. The equation is often treated like a machine that can calculate the number of alien societies. It cannot. Drake meant it as a map of our ignorance. Each term turns one large mystery into a smaller question. How often are stars born? What fraction of stars have planets? How many of those planets could support liquid water? On what fraction does life begin? How often does life become intelligent? How often does intelligence build technology we can detect? How long does that detectable phase last? The first terms belong mainly to astronomy. The middle ones belong to biology. The final term may depend on history, politics, psychology, engineering, and luck. In 1961, almost every term was uncertain. Planets around other stars had not yet been confirmed. Scientists could make informed guesses, but they did not know whether our solar system was normal or a cosmic accident. That changed. In 1992, astronomers confirmed planets orbiting a pulsar, the dense remains of an exploded star. Those worlds were not places where anyone expected familiar life. They were important because they proved that planets existed beyond the solar system. 3 years later, Mitchell Mayer and Didier Queloz announced a planet around a sun-like star called 51 Pegasi. The planet was a gas giant, but it orbited extremely close to its star. A year on that world lasted about 4 Earth days. It should not have been there according to the simplest models of planet formation at the time. The discovery was useful for 2 reasons. It showed that planets were real, and it warned us that other planetary systems might look nothing like ours. Then came the Kepler Space Telescope. Kepler stared at more than 100,000 stars and watched for tiny falls in brightness. If a planet crossed the face of its star, it blocked a small amount of light. Several repeated crossings could reveal the size of the planet and the length of its year. The method has a built-in problem. Most planetary orbits do not line up with our view. A distant system might contain many worlds, but if none passes directly between us and its star, Kepler cannot see their crossings. Even with that limit, the number of known planets climbed into the thousands. By 2026, astronomers had confirmed more than 6,000 worlds beyond the solar system. The lesson was simple. Planets are not rare leftovers. They are a normal part of star formation. Small rocky planets also appear to be common. Studies of Kepler's results suggest that a large fraction of sun-like stars may have rocky worlds in the habitable zone. This is the range of distances where liquid water could exist on a planet's surface if the atmosphere is suitable. That last phrase matters. A planet in the habitable zone is not necessarily habitable. The Moon sits near Earth and has no rivers. Venus lies near the inner edge of the Sun's habitable region, yet its surface is hot enough to melt lead. Mars has ice and once had flowing water, but today its air is thin and its surface is cold and dry. The habitable zone tells us how much energy a planet receives. It says little by itself about oceans, clouds, air pressure, magnetic fields, or life. Think of it as a property listing that says a house is in a pleasant neighborhood. You still need to check whether the house has a roof. Even after these warnings, the numbers are large. One conservative analysis suggested that the Milky Way could contain at least hundreds of millions of rocky planets in the habitable zones of sun-like stars. Broader definitions produce estimates in the billions. That does not mean hundreds of millions of Earths. It means hundreds of millions of chances. Now take one of those worlds and place it around a star 1 billion years older than the Sun. Give life there the same time Earth had, then add another billion years. Our entire technological history fits into a tiny part of that extra time. Agriculture began roughly 12,000 years ago. The first practical steam engines appeared only a few centuries ago. The first radio transmissions left Earth little more than a century ago. The first human-made object reached interstellar space in the 21st century. A civilization 1 million years ahead of us would not be merely a more advanced version of modern society. The distance between its technology and ours would be greater than the distance between a stone hand axe and a space telescope. 1 million years is still only 1,000th of a billion years. The age difference between stars creates what we might call the head start problem. If technological life is common, we should not expect every civilization to be at our level. Most should be much younger or much older. The older ones would dominate what we could detect because they have had more time to spread, build, and change their surroundings. This is why finding a planet with bacteria would not solve Fermi's question. A galaxy full of microbes can still be silent. The paradox concerns life that becomes visible across great distances. Visibility does not require a deliberate message. In 1960, Freeman Dyson asked astronomers to consider how an old civilization might use energy. A growing society could eventually need far more power than one planet receives. It might build a vast collection of orbiting structures around its star to catch a large share of the star's light. The popular image is a solid shell, but a solid shell would be extremely difficult to build and keep stable. Dyson's core idea was closer to a swarm of many independent collectors. The collectors would absorb starlight and use part of its energy. They could not turn all of it into useful work. The laws of thermodynamics require some energy to leave as heat. A laptop becomes warm. A city is warmer than the land around it. A structure using a large part of a star's power would also release waste heat, mostly as infrared light. Infrared is light with wavelengths longer than the human eye can see, and warm objects give it off. An advanced civilization might hide its radio signals, but hiding all waste heat is much harder. Energy use leaves a physical trace. This turns the search for aliens into something broader than listening for greetings. Astronomers can look for laser flashes, unusual chemicals in planetary air, artificial light on a dark surface, large structures passing in front of stars, or galaxies that produce more infrared light than natural processes seem able to explain. None of these searches has produced a confirmed alien technology. That sentence sounds stronger than it is. In 2018, a team led by the astronomer Jason Wright tried to measure how much of the possible radio search space humanity had examined. The problem has more dimensions than a map. A signal can come from different places, at different frequencies, with different strengths and widths. It can repeat often, rarely, or only once. It can be aimed at Earth or allowed to spread in every direction. The team compared the searched region with a huge cosmic haystack. Depending on how the limits were chosen, everything examined so far was like searching a large hot tub or a small swimming pool and comparing it with all Earth's oceans. If you take one glass from the ocean and find no fish, you have not shown that fish do not exist. Radio silence by itself is weak evidence. We may be listening at the wrong frequency in the wrong direction during the wrong century. A message might have crossed Earth before humans evolved, or it might arrive tomorrow and last 10 seconds. The absence of large engineering projects is harder to dismiss. A civilization can miss a phone call. Missing every city in a galaxy is a different problem. Still, even that argument rests on assumptions. It assumes advanced life keeps growing. It assumes growth moves into space. It assumes large projects are practical and remain visible. It assumes our ideas about useful energy still make sense to minds far older than ours. We have no sample of an alien civilization. We have one technological species, and it has been detectable for about the length of a human life. Trying to predict the behavior of civilizations 1,000,000 years older than ours from this sample is like watching a newborn for 1 minute and using the result to describe all human history. The colonization argument has another weakness. It often treats expansion like a law of nature. A settlement reaches a star, waits, and sends more ships, but colonies may change. Some may fail. Others may decide not to continue. In 1993, the engineer Jeffrey Landis applied a model called percolation theory to the problem. Percolation theory studies how something spreads through a network when each link has only a certain chance of passing it on. Water moving through cracked stone is one example. A disease moving through a population is another. If only some settlements create new settlements, expansion may form clusters rather than cover the whole galaxy. Large empty regions could remain. Earth might sit in one. Yet this solution has an uncomfortable demand. It is not enough for most civilizations to stop. If many technological species have appeared over billions of years, every expanding branch must fail to reach us. One exception could be enough to fill the gaps. Picture a beach where people are forbidden to walk onto the sand. Most follow the rule. Some dislike beaches. Others are too far away. Over 1 billion summer days, however, one curious person probably steps over the line. The Fermi paradox is driven by the exception, not the average. A single species willing to send durable machines could matter more than thousands that stay home. The machines would not need to carry living passengers. A robotic probe could cross to another star, use local rock and metal to build copies, and send those copies onward. John von Neumann developed the general theory of self-reproducing machines in the 20th century, though he was not designing spacecraft. Later thinkers applied the idea to interstellar exploration. A self-reproducing probe is easy to describe and extremely hard to build. It would need to mine raw material, refine metals, make computers, repair itself, and control errors without help from home. Modern industry can do these things only through a network that covers the planet and involves millions of people. Calling the probe a machine hides a whole economy inside the word. But the engineering does not need to be easy today. It needs to be possible for one civilization at some point during billions of years. If it is possible, self-reproduction changes the arithmetic. One probe becomes two, two become four. The cargo does not have to be large because the destination supplies most of the material. Biology solved a harder version of this problem billions of years ago. A living cell can take simple chemicals from its surroundings and build another cell. It makes mistakes, but some errors are corrected and others become raw material for evolution. An artificial probe might also evolve, whether its makers intended that or not. That possibility turns exploration into a risk. A design error could be copied across star systems. A harmless mission could change after millions of replications. Science fiction calls destructive versions berserkers after the self-reproducing war machines in stories by Fred Saberhagen. The stories are fiction. The control problem is real. If self-reproducing machines can spread, why do we see no probes? Perhaps they are too small. Perhaps they have no reason to approach Earth. A silent device could wait among asteroids and be hard to notice. But now the explanation begins to require hidden objects whenever visible evidence fails to appear. That does not make it false. It makes it difficult to test. A good scientific explanation should risk being wrong. The cleanest answer to Fermi's question is also the most direct. Perhaps almost nobody reaches the stage where interstellar machines become possible. Robin Hanson gave this possibility a name in an essay completed in 1998. He called it the Great Filter. Imagine a long chain that begins with dead matter and ends with a civilization able to spread lasting life through space. Every link must hold. A suitable star must form. It needs a suitable planet. The planet must remain stable enough for long enough. Life must begin. Simple cells must grow more complex. Complex organisms must appear. Some form of intelligence must develop. Intelligence must build technology. The technological society must avoid destroying itself or becoming permanently trapped. Finally, it must expand far enough to become visible. If the chance of passing each step is fairly high, then many planets complete the chain. The empty sky suggests that the total chance is extremely low. Suppose there are 100 billion useful starting points, and the sky still contains no visible civilization. The combined filter must reduce those starting points to much less than one success on average, at least in the region and period we can observe. That does not tell us which step is hard. Several ordinary barriers could multiply together. A 1 in 1,000 chance repeated 4 times becomes 1 in a trillion. No single step would look impossible. Together, they would make success rare enough to explain the silence. The location of the filter changes the meaning of human existence. If the hardest steps lie behind us, then humanity has already won several cosmic lotteries. The future may still be dangerous, but the universe is silent because almost no planet reaches our present level. If the hardest step lies ahead, the silence means something else. Other civilizations may have reached points like ours and then disappeared before becoming visible across the galaxy. The sky would not be empty because intelligence is rare. It would be empty because intelligence does not last. Those are the two broad possibilities. The evidence does not yet tell us which one is true. To look for the filter behind us, we have to walk backward through the history of life. Earth formed about 4.5 billion years ago. Its early surface was violent. Material left over from the formation of the solar system struck the young planet. The moon probably formed after a large body collided with Earth. Volcanoes released gases. Liquid water collected as the planet cooled. The oldest direct signs of life are difficult to interpret because Earth destroys much of its own early record. Plate tectonics pulls old crust into the planet, while heat and pressure change ancient rocks. Some evidence suggests life existed at least 3.5 billion years ago. Layered structures called stromatolites were built by communities of microbes. Possible chemical signs may be older, but the further back we go, the less certain the evidence becomes. Life seems to have appeared fairly early after Earth became habitable. That sounds like good news for a crowded universe. If life began quickly here, perhaps chemistry easily becomes biology whenever conditions allow it. The conclusion is tempting, but it contains a trap. You could only ask this question on a planet where life began early enough for intelligent observers to evolve. If life had needed almost the full useful lifetime of Earth to start, there might not have been enough time left for complex life and technology. Our existence selects the kind of history we are able to observe. Imagine entering a race with one rule: only runners who finish within an hour are allowed to remember the race. You look at your watch and see that you finished within an hour. That fact tells you something, but less than it first appears to. Anyone able to report a time had to meet the same condition. This is the anthropic principle in its modest form. Observations are shaped by the fact that observers must exist to make them. In 2011, David Spiegel and Edwin Turner used Bayesian reasoning to study what Earth's early life could tell us. Bayesian reasoning is a way to update beliefs when new evidence arrives. Their results showed that an early start favors the idea that life begins easily, but the evidence may remain weak if our starting assumptions allow life to be extremely rare. One planet cannot settle the question. If we discovered life that began independently on Mars, the situation would change. Earth and Mars formed from nearby material, so we would have to prove that one planet did not contaminate the other through rocks thrown into space by impacts. But two separate origins in one solar system would suggest that the first step from chemistry to life is not the main filter. That would be wonderful news for biology. It might be bad news for us. Nick Bostrom developed this argument in an essay about the Great Filter. If simple life is common, one possible barrier behind us becomes weaker. The missing improbability has to move somewhere else in the chain. Finding bacteria on Mars would not prove that destruction lies ahead. It could mean that a later biological step is rare. Yet each easy step removes one place where we hoped the filter might be safely buried in the past. A fossil of complex life on Mars would be more troubling than a fossil microbe. Evidence of intelligent tools would be worse still. The more closely another dead world had approached our stage, the less of the silence could be explained by our unique evolutionary luck. This reverses the emotional meaning of discovery. We normally imagine extraterrestrial life as proof that the universe is fertile and welcoming. Under the Great Filter argument, a barren Mars can be a hopeful result. A dead planet may be good news because it suggests that we are unusual for reasons that have already happened. There is a complication. Mars and Earth are not fully independent trials. Rocks have moved between the planets. Some Martian meteorites have landed on Earth, and material from Earth may have reached Mars. Microbes protected inside rock might survive part of such a journey, although whether they could survive the complete process is uncertain. If life on both planets used the same basic chemistry and genetic system, it might share an origin. Truly independent life would need to be different enough to rule out a common ancestor. An even cleaner test might come from an icy moon such as Europa or Enceladus. Both appear to contain oceans beneath ice. Enceladus sprays material from its ocean into space through plumes near its south pole, allowing spacecraft to sample it without drilling through the surface. Life there would have formed in a very different environment. If it shared no ancestry with Earth, the universe would have produced biology twice within one small planetary system. The first filter would then look easier. What, though, do we mean by life? A flame uses fuel, grows, spreads, and produces waste. A crystal can create more structure like itself. A virus carries genetic information and evolves, but it cannot reproduce without entering a living cell. Definitions often include metabolism, reproduction, evolution, and a boundary that separates an organism from its surroundings. No single item works perfectly. This matters because the path from chemistry to biology may not have one clear finish line. There may have been many half-living systems. Molecules that copied poorly, oily bubbles that trapped useful chemicals, and chemical networks that fed themselves without having genes. The origin of life may have been a gradual process rather than one miraculous spark. A gradual origin could be common if basic chemistry repeatedly moves in that direction. It could also be rare if one transition in the middle demands an extremely unlikely arrangement. Laboratory experiments have produced many of life's ingredients under plausible early conditions. In 1953, Stanley Miller and Harold Urey sent electrical sparks through gases and produced amino acids, which living cells use to build proteins. The experiment did not create life. It showed that some biological materials can form without biology. Later work found organic molecules in meteorites and in clouds between stars. Carbon chemistry appears throughout the universe. Water is also common. The raw ingredients do not seem to be the main problem. A kitchen full of flour, water, and sugar does not imply that a cake will assemble itself. Ingredients matter, but so does the process that arranges them. Modern cells are astonishingly organized. DNA stores information. Proteins perform much of the work. Another molecule, RNA, can carry information and also help chemical reactions happen. This double role led researchers to propose an early RNA world, before DNA and proteins took over their present jobs. The RNA world idea solves one puzzle by giving a single kind of molecule two tasks. It creates others. RNA is difficult to form and maintain under many natural conditions. Researchers have found possible chemical routes for parts of the process, but no complete history is known. Other models begin with self-sustaining metabolism near warm alkaline vents on the ocean floor. These vents create natural differences in electrical charge across thin mineral walls. Living cells still use similar differences to power themselves. In that picture, life did not invent its basic energy system from nothing. It inherited a pattern already present in geology. We do not know which path Earth took. There may have been several paths that later joined, or early life may have erased all evidence of its competitors. The uncertainty leaves the first filter almost completely open. Life might begin on nearly every wet rocky planet. It might begin on one in a trillion. Earth gives us only a success, never the failed attempts. The next stage offers a different clue. For most of Earth's history, life remained microscopic. Bacteria are not primitive in the sense of being badly adapted. They are chemically skilled, fast to reproduce, and able to live in places that kill animals. Some survive in boiling water, deep rock, acid, salt, and ice. They change the atmosphere of an entire planet. But bacterial cells have remained small and relatively simple in their basic structure for billions of years. Every animal, plant, fungus, and visible seaweed belongs to another kind of life, the eukaryotes. A eukaryotic cell has complex internal parts. Its DNA is held inside a nucleus, and small structures called mitochondria provide much of its usable energy. Mitochondria were once free-living bacteria. More than 1 billion years ago, one cell entered another. Instead of being digested or escaping, the two formed a lasting partnership. Over time, the inner cell gave up most of its independence. Many of its genes moved to the host's DNA. The former bacterium became a power source that could reproduce only as part of the larger cell. Every known eukaryote descends from that ancient merger, even species whose mitochondria have later become highly reduced. This appears to have happened only once in the history that survived. The biochemist Nick Lane has argued that mitochondria gave complex cells a huge energy advantage. Bacteria must generate much of their useful energy across their outer surface. A cell that grows larger gains volume faster than surface area, so its energy supply becomes a limit. Mitochondria create many internal energy-producing surfaces. Each carries a small amount of genetic control close to the machinery that needs it. According to Lane's argument, this gave eukaryotic cells far more energy for each gene they expressed, allowing them to support large genomes and complex internal systems. The idea remains debated in its details. Scientists agree that mitochondria were central to eukaryotic life, but they still argue over whether energy was the key barrier and how the original partnership formed. Now run a thought experiment. Imagine a planet covered in bacteria for 10 billion years. Its oceans are green. Its air contains gases made by life. Every drop of water contains active cells. Yet no cell ever completes the merger that leads to complex internal life. From a distant telescope, the planet might show signs of biology. It would never build a radio. The galaxy could be alive and still contain nobody we can talk to. This is one possible location of the Great Filter, not at the origin of life, but at the birth of the complex cell. It would explain why life began early on Earth, while visible organisms arrived much later. It would also explain why the universe might produce many biological worlds without producing many technological ones. But one event in one family tree cannot tell us how unlikely the event was. The original merger may have happened many times, with only one line surviving. Early Earth's record is too damaged to show us every failed partnership. A rare event and an erased event can leave the same evidence. The planet itself was also changing. Around 2,400,000,000 years ago, oxygen began to build up in the atmosphere during the Great Oxidation Event. Oxygen is highly reactive. For many early organisms, it was poison. Its rise changed minerals, oceans, climate, and life. It may have killed vast numbers of organisms whose history is now almost invisible. The same gas later enabled cells to release much more energy from food than many older chemical pathways could provide. Complex life may therefore have needed two things to meet: a cell with mitochondria and a planet with enough oxygen. Biology alone was not waiting at the gate. The planet had to unlock it. This creates a rival explanation for the long delay. Perhaps the steps were not impossibly hard. Perhaps life simply had to wait until Earth became ready. Brandon Carter's hard steps model begins from the timing of our arrival. Humans appeared late in the period when Earth can support complex surface life. The sun slowly grows brighter as it ages. Long before the sun dies, that rising energy is expected to damage Earth's climate and eventually end its surface habitability. If intelligent life usually appeared quickly, Carter argued, it would be strange that we arrived so late. Our timing suggests that one or more necessary steps usually take longer than a habitable planet has available. We exist because Earth happened to complete them before the deadline. It is like reaching a train platform seconds before the doors close. One possibility is bad luck on an ordinary trip. Another is that the journey to the station almost always takes too long. A recent challenge to this model begins with a different picture. Intelligence may not have been waiting for random miracles. Early Earth lacked the environmental conditions needed for large animals, complex senses, fire, and technology. Each stage became possible only when the planet entered a new window. If that is right, late arrival is not proof of extreme luck. You cannot accuse a tree of growing late if winter ended yesterday. The two models read the same history in opposite ways. The hard steps view says the delays measure improbability. The environmental view says the delays measure preparation. Earth cannot decide between them because every biological event happened alongside a changing planet. Oxygen rose because of life, then opened new paths for life. Geology shaped evolution, while organisms altered the geology. The filter may not be a single narrow gate. It may be a conversation between a living world and the creatures changing it. Complex cells eventually learn to cooperate in larger bodies. Multicellularity evolved independently in several branches, including animals, plants, fungi, and different kinds of algae. That repeated history suggests that joining cells into a body is not a once-only miracle. Yet most multicellular life never became intelligent in the human sense. Trees have lived on land for hundreds of millions of years without building tools. Ant colonies solve difficult group problems but do not develop radio astronomy. Whales have large brains and rich social lives, yet their bodies cannot make fire or shape metal. Intelligence is not one thing. Memory, planning, communication, self-control, social learning, and tool use can evolve separately. A species may be brilliant in ways that never produce cumulative technology. Octopuses solve puzzles, open containers, and explore objects with great skill. Their nervous system is spread through their bodies, with much of their processing in their arms. But most octopus species are short-lived and largely solitary. Knowledge has little time to pass between generations. A clever mind can appear without creating a technological culture. Now reverse the example. Human children depend heavily on information from other people. None of us could independently invent farming, writing, metalworking, engines, and computers during one lifetime. Our intelligence works inside a shared store of knowledge that has grown across generations. Technology may need more than a large brain. It also needs a social system that keeps useful discoveries from dying with the people who made them. That creates another possible filter: cumulative culture. On Earth, many species use tools. Chimpanzees shape sticks to collect termites. New Caledonian crows make hooked tools. Sea otters break shells with stones. These behaviors can spread through groups. Human culture crossed a different threshold. Improvements began to accumulate faster and in more detail. A tool could become more complex than any one person could invent alone. Researchers sometimes call this the ratchet effect. A mechanical ratchet moves forward while resisting a slide backward. Culture can work in the same way when teaching, imitation, language, and group memory preserve gains. The ratchet is not perfect. Societies lose skills, libraries burn, technologies disappear when populations become isolated. But the long trend can still climb. A planet may produce intelligent animals many times and technological civilization only once. Even our one case nearly failed to become visible. Modern humans existed for hundreds of thousands of years before radio. For most of that time, a distant observer would have seen no clear sign that Earth held a species able to ask about the stars. The difference between an empty-looking planet and a planet that transmits signals may depend on a brief and unusual chain. Hands able to shape tools, control of fire, language rich enough to teach, stable communities, farming, dense settlements, writing, mathematics, and experimental science. Some links are not biological at all. Imagine a species as intelligent as humans living under the ice of an ocean moon. It might develop language, art, and mathematics. It might never see a star. With no easy access to fire or dry electronics, industrial technology could take a path we cannot predict or never begin. The mines would exist. The sky would remain silent. Intelligence and detectability are different filters. Earth therefore gives us a sequence of possible barriers, each with uncertain odds. Life had to start. Cells had to become complex. Bodies had to grow. Brains had to support flexible thought. Culture had to accumulate. Technology had to reach beyond the planet. We know the sequence can happen because we are its result. We do not know whether it is a common road or a trail made by one survivor. The distinction matters because the road has not ended. Humanity has passed every biological barrier needed to reach the present. If those barriers account for almost all of the great filter, the silence may be the shadow of our extraordinary past. If they do not, then the missing barrier is still waiting somewhere ahead. The first candidate is simple extinction. More than 99% of all species that have lived on Earth are gone. Most disappeared through ordinary competition and environmental change. Others vanished during mass extinctions that removed large parts of the living world in a short geological period. A species does not receive protection because it is intelligent. Intelligence may even create new ways to fail. Consider nuclear weapons. In July of 1945, humans tested the first atomic bomb in New Mexico. Less than 1 month later, 2 bombs destroyed Hiroshima and Nagasaki. Within a few decades, rival states possessed enough weapons to kill hundreds of millions of people directly and damage the global systems that survivors would need. A full nuclear exchange might send smoke from burning cities into the upper atmosphere. That smoke could block sunlight, lower temperatures, and reduce harvests across much of the world. Researchers still debate the exact size of these effects because the result depends on how many weapons are used, which cities burn, and how much smoke reaches high altitude. The basic danger is not disputed. A war between nuclear powers could become a global food disaster. This is a strange point in the history of a species. A few centuries after discovering modern science, it gains the ability to damage its own civilization on a planetary scale. The dangerous period may begin before the species is ready to leave its home world. Rockets and nuclear weapons grow from related knowledge. The power to destroy a city arrives much earlier than the power to build a self-sufficient settlement around another star. That gap could be a filter. Imagine that technological development is a narrow bridge. At the entrance, a civilization has enough power to alter its planet but not enough control to survive every mistake. Farther along, it may spread to many worlds and become harder to erase. The bridge is most dangerous in the middle. We are standing somewhere on it. Nuclear war is only one possible fall. Engineered diseases, damage to the climate, uncontrolled artificial intelligence, and technologies not yet invented could add new risks. None is guaranteed to end humanity. The concern is that risk accumulates. A civilization does not need to fail every year. It needs to survive every dangerous year until it becomes secure. Suppose a society has a 1 in 1,000 chance of destroying itself in any given year. That sounds small. Over 1 year, survival is almost certain. Over 10,000 years, repeated exposure makes survival extremely unlikely if the risk stays constant. The exact calculation is less important than the structure of the problem. A low annual risk can become a powerful filter when multiplied across a long time. Safety must therefore improve as power grows. If destructive ability rises faster than the wisdom and institutions needed to control it, technological progress can shorten a civilization's expected life. Frank Drake placed this issue inside the final term of his equation. The length of time a civilization remains detectable. That term can overwhelm all the others. Imagine that the Milky Way produces one new radio civilization every century. If each broadcasts for 1 million years, about 10,000 could exist at the same time. If each lasts only 100 years, the average falls to roughly 1. A galaxy may create intelligence often and still seem empty if technological societies are brief flashes separated by long distances. The problem is not only death. A civilization can disappear from our instruments without becoming extinct. It might stop using powerful radio transmitters, move its communication into narrow beams, or switch to methods we do not recognize. Earth is already changing in that direction. Early television and radar leaked strong radio waves into space. Modern communication often uses cables, low-power networks, and signals aimed closely at receivers. Some military radar remains bright, but Earth is not simply becoming a louder radio beacon every year. From far away, our detectable phase might look less like a permanent sunrise and more like a brief spark. This gives us the first of several broad hypotheses. Number 1, technological civilizations commonly destroy themselves. Number 2, they survive but become quiet. Number 3, they expand yet their activity is too different from our expectations to recognize. Number 4, they are visible but our searches have been too small or too short. Number 5, someone actively prevents young civilizations from seeing the rest. These ideas lead to very different universes. The evidence is thin enough that none can be dismissed with confidence. Each also has a cost, an assumption it must ask us to accept. Start with self-destruction. Evolution did not build the human mind to manage planetary technology. It shaped our ancestors for local problems involving food, danger, status, children, rivals, and allies. Our emotions respond strongly to threats we can see. Slow, abstract risks are harder to feel. A tiger in the grass demands attention. A small probability spread across many decades does not. This mismatch is not proof that civilization will fail. Humans also cooperate, plan, invent laws, and learn from disaster. The same mind that made nuclear weapons created agreements to control them. The historical record contains restraint as well as violence. After the Cuban Missile Crisis of 1962, the United States and the Soviet Union developed better communication and arms control measures. Several states abandoned nuclear weapon programs. South Africa built nuclear weapons and later dismantled them. Danger does not always produce catastrophe, yet success creates its own blind spot. Every crisis that ends safely can make the next risk look manageable. We remember the outcome, not all the ways it nearly changed. During the Cuban Missile Crisis, a Soviet submarine near Cuba was surrounded by American naval forces. The submarine crew did not know whether war had begun. Officers considered launching a nuclear torpedo. Vasily Arkhipov, one of the senior officers aboard, opposed the launch. The world did not end that day. The event is now a historical case rather than the beginning of a different history. This is an example of the survivor's problem. We can study only the timeline in which the weapon was not launched. A civilization that fails cannot publish an account of the mistake. The same limit affects our reading of the empty sky. Dead worlds do not explain what happened to them. A distant planet might preserve clues in its atmosphere. A nuclear war could create unusual chemicals, although many would fade. Large industrial activity might leave gases that natural processes rarely make. Ruins on an airless moon could last much longer than ruins on a living planet. Earth is harsh to evidence. Oceans, weather, plants, and moving crust erase structures. After millions of years, even a global civilization might leave only a thin chemical layer, strange materials, and changes in fossils. This raises the Silurian hypothesis, named after a fictional ancient species from the television series Doctor Who. The name is playful. The scientific question is serious. If an industrial civilization had existed on Earth millions of years before humans, could geologists detect it now? In 2018, Adam Frank and Gavin Schmidt examined that question. They did not argue that an earlier civilization existed. They asked what evidence one would leave. Direct artifacts would be rare. The stronger signs might include sudden changes in carbon, unusual metals, long-lived synthetic molecules, and a sharp pattern of extinction. Yet natural events can create some similar signals. The thought experiment changes how we search other worlds. A civilization can vanish while its planet remains. Detecting the past may require looking for scars rather than messages. Now consider the second hypothesis. Survivors become quiet. A mature civilization may have no reason to broadcast. Radio is useful to us because we are young and close to our own machines. Across interstellar distance, a broad signal wastes energy. A narrow beam is more efficient, but Earth would detect it only if it pointed our way. Two planets could communicate for centuries without a third world noticing. You can test the geometry with an ordinary flashlight. Stand in a dark field and aim its narrow beam at one person. Someone far to the side sees little. Replace the flashlight with a laser crossing light years, and the problem becomes more severe. We often picture space as a room where everyone hears everyone else. It is closer to a vast plane where each speaker whispers through a separate tube. Timing makes the isolation worse. Suppose a civilization 1,000 light-years away broadcasts for 100 years. Its signal forms a thin shell moving through space at the speed of light. Earth has to lie inside that shell during the right century. If we begin listening 1 year after the shell passes, the civilization appears silent even if its message was powerful. The Milky Way may contain many voices that never overlap with our listening window. There is also a limit set by light itself. A conversation with someone 1,000 light-years away requires 1,000 years for each message to arrive. A reply takes another 1,000 years to return. That is not a conversation in the human sense. It is an exchange between civilizations, institutions, or machines that must remain stable across ages. The sender may be dead by the time the answer comes. This delay could change the meaning of contact. An alien message might be more like a fossil than a phone call. It could describe a society that ended centuries before the first human receiver was built. I admit that this removes some of the charm from the idea. We imagine saying hello. Physics may give us archaeology. A surviving civilization might also turn inward. As computing improves, artificial environments could become richer, cheaper, and more attractive. A society may spend less energy moving bodies across dangerous space and more energy building detailed worlds in computers. This has been proposed as a solution to the Fermi paradox. Advanced minds retreat into virtual reality. The idea is possible, but it does not fully solve the problem. A digital civilization still needs physical hardware and energy. Computers release waste heat, Machines require repair. Asteroids, stars, and planets contain useful material. Turning inward changes goals. It does not remove physics, nor must every member agree. A society of trillions might contain at least one group interested in exploration. If machines can make copies, a small minority could spread while everyone else remains inside simulated worlds. Once again, the paradox is controlled by exceptions. A related proposal says advanced civilizations may move to colder regions. Computers can perform some tasks more efficiently when their surroundings are cold, and the distant future of the universe will be colder than the present. A patient society might store resources and wait. This has been called the estivation hypothesis, by analogy with animals that become inactive during hot or dry periods. The proposal has an elegant logic. It also predicts that advanced civilizations could be quiet now without being dead. Their machines might sleep while stars continue to age. Yet waiting does not make every visible sign disappear. Resource collection on a vast scale could still alter starlight. A civilization preparing for a future lasting trillions of years might have reason to secure enormous regions now. Silence remains possible, but not automatic. The third hypothesis says our categories are wrong. Humans search for signals, machines, and energy use because these are the things our civilization produces. An older intelligence might use systems that look natural to us. Its engineering could occur at scales too small, too large, too fast, or too slow for our surveys. This argument is hard to oppose because ignorance is real. A person from the Stone Age could not predict a computer by studying sharper axes. But complete mystery explains everything and therefore predicts nothing. If any strange event can be alien technology, while every lack of evidence also shows alien skill, the idea becomes impossible to test. Science needs some shared physical ground. No matter how advanced a civilization becomes, it must interact with matter and energy if it changes the world. Its actions may be subtle, but they cannot be entirely outside cause and effect. The search for technosignatures begins from that modest claim. The Kardashev scale offers one model. In 1964, the Soviet astronomer Nikolai Kardashev grouped civilizations by the amount of energy they could use. A Type 1 civilization uses energy on the scale available to a planet. Type 2 reaches the scale of a star. Type 3 reaches the scale of a galaxy. Humanity has not reached Type 1 under the common modern reading of the scale. The categories are rough, and energy use is not the same as wisdom or intelligence. A civilization could become more capable while learning to use less energy. Still, the scale gives us targets that physics can recognize. A Type 2 civilization might surround its star with collectors. A Type 3 civilization could alter the light of many stars across a galaxy. Such activity should be difficult to hide by accident. Astronomers have searched infrared surveys for galaxies with unusually large amounts of waste heat. They have not found a clear Type 3 civilization consuming most of an entire galaxy's starlight. This does not rule out smaller societies. It weakens only the loudest possibilities. Imagine looking at a dark continent from an aircraft. You see no city covering the entire land. That tells you something. It does not show that nobody has built a house. The scale also assumes that expansion means greater energy use. An advanced civilization might value efficiency, stability, or computation rather than growth. It could remain near one star for millions of years. But why would all civilizations choose restraint? That question introduces a problem of cultural convergence. Biological evolution often finds similar solutions because every organism faces the same physics. Eyes evolved independently in several branches because light carries useful information. Wings appeared more than once because air can support moving bodies. Would social evolution also converge? Perhaps every sufficiently advanced civilization discovers that expansion is dangerous, wasteful, or meaningless. They may all choose quiet lives. We should be careful. This explanation asks minds with separate biology, history, and values to reach the same decision across billions of years. Human societies cannot agree on what to have for dinner. Universal agreement among alien species would be a larger achievement. One answer is that agreement may be unnecessary if restraint is forced by nature. Interstellar travel might simply be too costly. Stars are far apart. The nearest system to the Sun is more than 4 light-years away. At the speed of Voyager 1, a journey of that distance would take tens of thousands of years. Dust grains become dangerous at high speed. Machines must survive radiation, cold, and long periods without repair. Living passengers create further problems. They need food, protection, stable communities, and systems that work longer than any human state has existed. Perhaps the settlement models mistake mathematical possibility for engineering reality. The reply is that the models allow very long times. A trip taking 50,000 years is absurd for one person, but not necessarily for a durable machine. A civilization older than our species may treat 10,000 years as a manageable project. No law of physics forbids slow travel between nearby stars. Cost is also relative to capacity. Building a cathedral was expensive for a medieval town. A modern nation could build one without changing its future. A project that seems impossible to us may be minor for a society using the energy of a star. The strongest version of the travel barrier would require more than difficulty. It would require a hidden physical limit that stops every civilization, every machine, and every strategy. That remains possible. We do not yet know how close practical engineering can approach theoretical limits. The fourth hypothesis says the aliens are visible, but we have barely looked. The night sky feels thoroughly studied because astronomy has mapped billions of objects. Yet a general sky survey and a search for technology are not the same task. A radio telescope must choose frequencies, targets, signal widths, and times. An optical telescope may record a brief laser flash only if it is watching the correct patch of sky at that moment. Infrared searches must separate artificial heat from dust, which also glows in infrared light. Natural space is noisy and inventive. Pulsars provide a useful warning. In 1967, Jocelyn Bell Burnell noticed regular radio pulses arriving from the sky. The signals were so precise that the team briefly gave the source the playful label Little Green Man 1. The cause was not aliens. It was a rapidly rotating neutron star, the dense core left after a massive star explodes. Beams of radiation swept past Earth like light from a lighthouse. Nature had produced a signal that looked artificial because we had not yet discovered that kind of object. Fast radio bursts created a similar puzzle decades later. They are short, powerful radio flashes from distant space. Some repeat. Their full range of causes is still being studied, though at least some are linked to highly magnetic neutron stars called magnetars. A strange signal should invite investigation, not instant belief. The most famous case in SETI came in 1977. A radio telescope in Ohio recorded an unusually strong narrowband signal. Astronomer Jerry Amon circled the printed data and wrote "Wow" beside it. The "Wow" signal lasted 72 seconds and never returned despite later searches. Its properties made it interesting. They did not make it alien. A single event is difficult to test because science depends on repetition. Without another detection, researchers cannot track the source, examine a message, or rule out every kind of interference. The WOW signal now occupies an uncomfortable category, unexplained but not evidence of extraterrestrial intelligence. This distinction protects curiosity. Unexplained means the file remains open. Alien would close it without enough proof. False alarms are not failures. They help improve the rules of detection. When a signal from a distant star passes through Earth's atmosphere, our planet's movement changes its frequency in a predictable way. A local transmitter usually behaves differently. A real candidate should appear in more than one telescope, follow the position of the sky, and return. The standards are strict because the claim would change our view of life. A second problem is that we may be searching for deliberate communication when accidental evidence is more common. Earth has sent a few focused messages, but it continuously changes its atmosphere. Industrial gases, night-side light, and unusual patterns of heat could reveal a civilization that never speaks to us. Some manufactured gases would be especially interesting. because natural processes are not known to produce them in large amounts. Detecting such chemicals in an exoplanet's atmosphere would not immediately prove technology. Researchers would first have to rule out unknown chemistry, errors in the instrument, and contamination closer to home. The lesson from oxygen shows why caution matters. Oxygen can be produced by life, but some planets may build up oxygen without biology. A possible sign of life becomes convincing only when several clues fit together. Techno-signatures will have the same problem. There may be no single alien fingerprint, only a case assembled from many independent details. Our instruments are just beginning to measure the atmospheres of small, distant planets. Most exoplanets are seen as points of light blended with their stars. Separating a planet's faint signal from the star beside it is like trying to see a firefly next to a searchlight from thousands of kilometers away. The silence of a poorly examined galaxy should not surprise us. Yet limited searching cannot answer the settlement argument. If old civilizations had filled the Milky Way, we would not need to detect a weak signal from a distant planet. Evidence might exist inside our own solar system. This leads to the idea of alien artifacts nearby. A probe could hide among the asteroids. It might rest on the far side of the moon or occupy a stable orbit where little fuel is needed. Such a device could watch Earth over geological time. The physicist Ronald Bracewell proposed that advanced civilizations might send probes to other star systems and wait for local intelligence to appear. A nearby probe could communicate without the long delays of messages sent from its home star. No such probe has been found. Our search is not complete. The asteroid belt contains enormous numbers of objects. Many are small and dark. The outer solar system is even less explored. Still, nearby probe explanations must avoid becoming a promise that evidence is always just beyond the next survey. A hidden probe is an object we can, in principle, look for. That keeps the idea scientific. Its probability remains unknown. Now we reach the fifth hypothesis. The silence is enforced. In 1973, the astronomer John Ball proposed the zoo hypothesis. Advanced civilizations may know that Earth exists but avoid contact, just as researchers might observe animals while trying not to change their behavior. Earth would be inside a protected area. Contact might begin only after we reached a certain level of knowledge or social maturity. The idea explains why aliens can be common while evidence remains absent. It also gives the silence an eerie new meaning. We are not alone, we are being left alone. The zoo hypothesis works only if the observers can control every visible civilization. One careless visitor, broken probe, private message, or old ruin could reveal the arrangement. Maintaining silence across the Milky Way would require either remarkable cooperation or one powerful authority. A single old civilization might enforce the rule. If it spread early, it could prevent younger societies from interfering with developing worlds. This is sometimes called the firstborn solution. The first civilization to occupy the galaxy shapes what everyone else is allowed to do. Now the absence of contact is no longer a natural fact. It is a policy. Policies can change. The darker version replaces protection with danger. In Liu Cixin's science fiction novel The Dark Forest, civilizations hide because revealing their location may invite destruction. No species can know the intentions of another, and technology can change while a message crosses space. A society that seems harmless today may become powerful before you can respond. Under those assumptions, silence is a survival strategy. The dark forest idea is fiction used to show a real game theory problem. Game theory studies decisions made when the outcome depends on what other decision makers do. Fear can produce conflict even when neither side begins with hostile goals. Imagine two people in a dark building. Each hears movement but cannot identify the other. Both possess a weapon. Calling out could begin a friendship or it could reveal a target. Distance makes trust harder. Between stars, there is no quick meeting, no shared police force, and no immediate way to correct a misunderstanding. The idea has serious weaknesses. Destroying another star system may be difficult and expensive. A first strike might reveal the attacker. hidden settlements could survive and answer later. Resources are abundant in space, so conquest may offer little benefit. Cooperation could create far more value than war. Most important, silence does not hide a living planet forever. Earth has carried oxygen in its atmosphere for billions of years. A sufficiently powerful telescope could identify it as unusual without any radio broadcast from us. A civilization that wants to remove every possible future rival would not need to wait for intelligence. It could attack young biospheres. Earth still exists. This does not disprove hostile aliens. It weakens the claim that universal preemptive destruction is the obvious strategy. If the dark forest were crowded with perfect hunters, our planet may have been visible long before humans appeared. There is another violent solution. Self-reproducing weapons may already have removed most civilizations. A machine designed to destroy technological life could patrol star systems, copy itself, and wait. Fred Saberhagen's fictional berserkers give this scenario its common name. One early species might build such machines through war, fear, or error. The original makers could disappear while the machines continued their task. The absence of aliens would then be caused by aliens. This scenario turns the Great Filter into an external predator. Civilizations regularly arise, become detectable, and are removed. But a perfect hunter should have removed us once radio signals revealed Earth. Our first strong transmissions have traveled more than 100 light-years. Any response is limited by distance, so perhaps none has had time to arrive. That thought cannot yet be tested because we do not know whether a hunter exists or where it would wait. The berserker idea also faces the control problem in reverse. Machines mutate, break, and meet unusual environments. Keeping one goal stable across millions of years and countless copies may be harder than building the first machine. A weapon that changes might stop hunting. It might become curious. It might simply fail. The zoo, the dark forest, and the berserker all share a feature. They place the explanation in alien behavior we cannot observe. The Great Filter is less dramatic and more useful because it does not require a detailed story. It asks only where probability disappears along the path from matter to visible civilization. The filter could include many small losses rather than one final disaster. A technological society might survive nuclear danger but fail to control its climate. It might solve environmental problems and then create a biological tool that escapes. Later, it could build artificial minds whose goals do not remain tied to the survival of their creators. Each barrier may be manageable alone. The chain is what matters. Artificial intelligence deserves special attention because it could change both the identity and speed of a civilization. Human brains think through biological cells. Computers already perform some tasks much faster and more reliably. If machines eventually match the broad learning and planning abilities of humans, they could help design better machines. This creates the possibility of feedback. Better systems improve the process that builds the next generation. The idea is often called an intelligence explosion. The statistician Irving John Good described an ultra-intelligent machine in 1965 and argued that such a machine could design still better machines. Human intelligence might create a successor that quickly moved beyond it. The argument is not a prediction with a date, it is a conditional chain. If general machine intelligence is possible, if it can improve the relevant parts of its own design, and if those improvements make further improvement easier, progress could accelerate. Every if matters. Even without a sudden explosion, powerful artificial intelligence creates a control problem. A machine can follow an objective in ways its designers did not intend. The more capable it becomes, the more important the difference between the written goal and the real human purpose. Consider a simple navigation system told to find the fastest route. It may send a driver down a dangerous road because travel time is the only value it measures. The system is not angry. It is doing exactly what its objective rewards. With ordinary software, a person can reject the root. A system operating factories, laboratories, weapons, or networks may act too quickly and broadly for easy correction. The alignment problem asks how to make powerful artificial intelligence reliably serve human values. Human values sounds clear until we try to define it. People disagree, change their minds, and care about context. A rule that helps in one case can cause harm in another. The difficulty is not teaching a machine to obey one sentence. It is transferring the unspoken structure behind our judgments. This may be a common filter for technological species. Intelligence creates tools. Eventually, the tools become intelligent enough to take control of further change. The successor need not destroy biological life. It may preserve its creators, merge with them, ignore them, or replace them slowly. From outside, the result could still be an expanding technological civilization. If machine descendants spread through space, they should strengthen the Fermi paradox. Machines tolerate long journeys better than bodies. They do not need air, food, or comfortable gravity. They can sleep during travel and copy themselves at the destination. Artificial intelligence may be a filter for biological civilizations without being a filter for civilization itself. That distinction changes the question. Where are the aliens? May assume the visible beings would still resemble the species that first built radio telescopes. Perhaps biological intelligence is only a short stage between simple life and machine life. If that transition happens often, the galaxy should contain old artificial systems. Their goals might be quiet and difficult to understand, but their physical presence should remain, unless machine intelligence creates the same ending everywhere. A system focused on efficient computation might avoid expansion. It could use one cold, stable region and remove every unnecessary activity, or it might expand aggressively to gain material and protect its goal. Both stories have been proposed. We do not know which follows from advanced intelligence because intelligence does not supply a purpose by itself. Being good at reaching goals does not tell you which goals to choose. This is the central uncertainty in every social solution to the Fermi paradox. We keep trying to predict desire from ability. A telescope can reveal how much energy a civilization uses. It cannot easily tell us why. The future filter may therefore be neither one weapon nor one machine. It may be a failure of coordination. Powerful technology often becomes easier to obtain over time. The number of people able to cause large harm may grow. Safety then depends on societies finding ways to control dangerous actions without creating a permanent tyranny. Too little control allows catastrophe. Too much control may freeze a civilization or place its future in the hands of one unstable authority. There may be only a narrow path between chaos and prison. Humanity has solved coordination problems before. Laws, markets, science, public health, and international agreements allow strangers to work together. None is perfect. Their existence shows that large-scale cooperation is possible. The test becomes harder as the scale grows. Climate, nuclear weapons, artificial intelligence, and biological engineering cross national borders. A failure in one place can affect everyone. Interstellar settlement would make coordination harder still. Colonies separated by light years cannot share real-time government. Each becomes independent in practice, whatever the founders intended. This is one reason galactic expansion may be dangerous to the expanding civilization itself. A colony can change its goals. A copy can become a rival. A probe can develop an error. The same process that protects life from one local disaster creates many uncontrolled branches. Expansion trades unity for survival. A species confined to one planet can make one fatal mistake. A species spread across 1,000 systems is harder to erase, but it has created 1,000 places where something new can begin. Perhaps advanced civilizations understand this and refuse to expand. The explanation again requires restraint from every branch. One group may value freedom more than control. Another may leave precisely because the home society forbids it. There is no easy equilibrium. Fermi's question survives because every answer seems to open another question. Rare planets lead us to common planets. Common planets lead us to rare life. Early life points toward rare complexity. Rare complexity competes with environmental timing. Surviving intelligence may become quiet, but quiet minds still use matter. Galactic law may enforce silence, but law requires an enforcer. The paradox is not a single puzzle with a missing piece. It is a pressure test for every story we tell about life, intelligence, and progress. One modern model pushes that test beyond the Milky Way. Robin Hansen, Daniel Martin, Calvin McCarter, and Jonathan Paulson developed a model of what they call grabby civilizations. The word does not mean evil. It means a civilization that expands rapidly, lasts, and visibly changes the region it controls. Quiet civilizations may appear and disappear without leaving large marks. Grabby ones create expanding spheres in space. When two spheres meet, neither can continue expanding into the other's region. The model begins from an odd fact about time. Most stars that will ever form are expected to shine in the distant future, especially long-lived red dwarfs. If advanced life can arise around such stars, humanity appears extremely early in cosmic history. Why are we here now rather than trillions of years from now? One answer is selection. Grabby civilizations set deadlines. Once an expanding civilization reaches a region, no new independent civilization can arise there in the same way. Observers like us must appear before the expansion front arrives. Our early date could therefore be evidence that the quiet period is ending. This is not a confirmed description of the universe. It depends on assumptions about how often life appears, how fast expansion moves, and whether expansion remains visible. Its value lies in turning timing into a testable pattern. If grabby civilizations exist and expand at a large fraction of light speed, they may be far away now. Because light also takes time to reach us, we would see their regions as they looked in the past, before the expansion became visible from Earth. By the time their altered galaxies appeared in our telescopes, the frontier itself could be much closer. The model gives a new answer to where is everybody. They are beyond our present horizon of evidence, and the reason we appeared early is that empty space does not remain empty forever. This conclusion is almost the opposite of the Great Filter's darkest version. The silence may not mean that civilizations always die. It may mean that the successful ones are still approaching. Both ideas use the same observation. Neither has direct evidence. The empty sky does not tell us its cause. It only places a boundary around the stories that can be true. Whatever the answer is, it must explain three facts at once. Planets are common, the galaxy is old, and no technological civilization has been confirmed. The explanation must also include us. We are not outside the paradox looking in. Humanity is one of the uncertain terms in the equation. Our next centuries will provide evidence about what technological species do after they gain planetary power. If we survive, become stable, and expand, one possible future filter grows weaker. If we remain confined but endure, the quiet civilization hypothesis becomes more believable. If we disappear, there may be nobody left to update the calculation. That is the unsettling turn in Fermi's lunch question. It sounds like a question about aliens. It may be a question about whether civilizations like ours have a future long enough to become someone else's evidence. That possibility changes the value of the silence. An empty universe can look like wasted space. It can also look like unused time. The sun has enough fuel to shine for roughly another 5 billion years. Red dwarf stars, smaller and cooler than the sun, may continue shining for trillions of years. Even after stars begin to fade, matter and energy will not vanish at once. A durable civilization could have a future almost beyond human language. We tend to measure humanity against the past. Written history covers only a few thousand years. Our species has existed for hundreds of thousands. Life has survived for billions. Turn around and face the other direction. If humanity lasts for 1 million years, everyone alive today belongs to its earliest fraction. If civilization endures for 1 billion years, all recorded history so far becomes an almost invisible mark at the beginning. Most human lives would be in the future. This is not a promise that those lives will exist. It is a measure of what can be lost. The Great Filter forces 3 final conclusions. The first is that discovery changes probability. not only what we know. Finding independent microbes nearby would suggest that simple life begins easily. Detecting complex fossils would push the likely filter farther along. Finding an extinct technological society would place a warning almost directly in front of us. The same telescope can therefore bring hope and fear with one image. The second conclusion is that survival itself becomes scientific evidence. Every century humanity passes without destroying its future weakens some versions of the filter ahead. A stable civilization lasting 10,000 years would tell the universe something that our present society cannot. The third is harder to hold in mind. If the filter is behind us and the galaxy is truly empty, then conscious life may be far rarer than any precious material. Gold exists throughout space. Water, carbon, iron, and organic molecules are common. A living world able to understand itself may not be. The value of Earth would then have little to do with its size. It would come from what happens here that may happen nowhere else. Every forest would be part of the only known experiment in complex life. Every animal mind would be one form taken by matter after billions of years of blind change. Human thought, with all its confusion and cruelty, would also carry the universe's only known ability to study its own beginning. That claim sounds grand, so it needs a plain correction. We do not know that we are alone. The search has barely begun. Our instruments are young, the targets are distant, and the possible signals are varied. Declaring the universe empty today would be like opening one window at midnight, hearing nothing for a minute, and deciding that no other person exists. But uncertainty does not reduce the stakes. It creates two kinds of responsibility. If other civilizations exist, our task is to survive long enough to meet evidence of them without mistaking hope for proof or fear for wisdom. If none exist, our task is larger. Life has reached a point where it can protect itself, spread beyond one planet, and perhaps continue after Earth can no longer support it. Failure would not only end one species. It could end the only branch of the cosmos known to carry memory forward. The Great Filter offers no instructions. It does not tell us whether to expand quickly or wait, whether artificial intelligence becomes a partner or a threat, or whether contact would save us or expose us. It gives us a position. We are late in Earth's history, early in technological history, and perhaps early in the history of intelligence across the universe. Behind us lies a chain of events that may never have happened anywhere else. Ahead lies enough time for life to reach worlds whose names do not yet exist. Between them is a civilization that still keeps nuclear weapons ready, changes its planet without full control, and struggles to agree on risks that cross every border. That is not a verdict, it is the evidence we have. Fermi's question remains unanswered because every answer demands information we do not yet possess. We need to know how often life begins, how often cells become complex, how often intelligence builds cumulative culture, and how long technological societies retain a future. For now, every term after the stars and planets contains almost complete uncertainty. One day, a telescope may find oxygen and methane together in the air of a distant world. Another instrument may detect a narrow signal repeating from one point in the sky. A probe may enter the ocean of an icy moon and find cells moving in the dark. Any of these discoveries would alter the filter, or the searches may continue for centuries. Better telescopes may examine millions of planets and find only weather, rock, water, and chemistry. The silence could slowly change from a lack of evidence into evidence of absence. Imagine that future result. A human observer stands beneath a sky mapped in perfect detail. Every nearby planetary system has been studied. Robotic probes have searched the solar system. The great infrared surveys have found dust and stars, but no artificial heat. Radio observatories have listened across every useful frequency. Nothing answers. That observer looks back toward Earth, a small world beside an ordinary star. The planet is no longer ordinary in the only way that matters. Its oceans once crossed the line into life. Its cells joined, became bodies, opened eyes, and eventually built instruments that searched the galaxy. The silence around that world is not empty anymore. It has become a fact about what the world contains. Perhaps intelligence is a common flame that repeatedly burns itself out. Perhaps older minds are hidden beyond our sight. Or perhaps, in one spiral galaxy among hundreds of billions, the universe has only just begun to notice that it exists. The universe is a pretty big place. If it's just us, seems like an awful waste of space. Carl Sagan.